Well, good day, everybody. Thank you. I'm very glad to be here. Partially because I really like the idea of fixing the incentive structure of publishing. I did not finish my PhD partially because several reasons, but one of the reasons was very frustrated with in the field that I was doing my research, the wrongest paper got the most citations through the incentive structure, and was very frustrating if you actually want to do science in the sense of I want to discover things that are true, and then you observe an incentive structure which is very much geared to doing scientism, something that looks like science but is really just I'm going to publish a bunch of papers that may or may not be true. So it's very exciting for me to see efforts here of fixing brokenness in the incentive structure. And my second company I started with a friend of mine, Sean Heelan, which was quoted on one of your slides. He did finish his PhD, but he shared all my my gripes. And it was so bad at the time that we had a diagram in my first company on the blackboard, which was correct, relevant, published, pick two. So I'm super excited about the format of this workshop. My talk is titled Reasons for the Unreasonable Success of Fuzzing. Now, perhaps I should talk a little bit about why I say it's unreasonably successful, but I'll speak a little bit about my personal history, which goes from being part of the late 1990s hacking youth culture, which for a variety of reasons really did not think that fuzzing was a very reasonable thing to do in the first place. And then as somebody who rejected fuzzing as a young man, over the years, I just had to realize I'm wrong. And this talk is a little bit about all the reasons why I had to correct my understanding of the world. Another thing is I've been staring, like everybody, I've been staring a lot at what's happening in ML, AI these days. I think there's a few lessons from the AI community about what they call the bitter lesson that can be translated to fuzzing and to program analysis. And it's a very bitter lesson in that sense. Anyhow, so the late 90s, early 2000s hacking culture was very much a standard teenage subculture as you find them in graffiti, in skateboarding, in breakdance, whatever. It's largely boys for whatever social reasons. And they're largely building some weird hierarchy external to society where they compete or cooperate, compete for status in some sense. And these communities build their own value systems that are often quite different from the broader value system of society. If you think about graffiti artists, very often the property damage you incur needs to be maximally visible in order to gain your reputation. And similarly, in the hacking community, status was acquired by either display of extreme brazenness or of unusual skill. It's a bit weird, like if you look at a bunch of different animal species, young dolphins bond like over doing stupid stuff together. And apparently these bonds last into adulthood. And the hacking community was somewhat similar to this. So what is the property of a community of a bunch of teenage kids competing for status? Teenagers, by and large, are time rich and cash poor. Like nobody has any money. Everybody has a lot of free time at hand. And back then, computers were almost unimaginably slow by today's standards. That's just the nature of exponential growth. So status in the community was linked to being hardcore in some way. Could mean individual abilities that were absurd. I can decompile this large assembly function in my head. Or I'm particularly brazen in the sort of machines I break into and the sort of source code I steal. So fuzzing as a technique violates that status competition, right? Because fuzzing by its nature has very little to do with what sort of hardcore skills you have and a lot to do with how much money you can bring to bear on a problem. So the bias in the community was very strongly against fuzzing because clearly you're not displaying skill. You're in the value system of that community. Clearly you're just a rich kid throwing money at the problem because you have a faster computer and you can't actually think. So the prevailing attitude in that community towards fuzzing was negative between ridicule and disdain. And quite literally, I was present in 2001 at a conference where just a group of drunk teenagers would crowd another researcher and yell at him, fuzz-tester, as a sort of insult. The I'm not sure whether the person understood what was going on at the time, but neither did the people yelling, right? So the interesting thing is that change arrived when people from a different subculture that had evolved separately arrived in the hacking community, and these were, funnily enough, the former spooks. So in the early 2000s, there was an exodus of a bunch of young ex-NSA security folks that, for a variety of bureaucratic reasons, left NSA. And they came from a very results-driven culture where if you found the bug, you win. And they came from a culture where compute was abundant and money was abundant, but was human brain power that was scarce. And it was largely the influx of these people into the broader hacking community that popularized fuzzing, which is interesting, right? Because you have two different cultural value systems that collide, and eventually, begrudgingly, very reluctantly, the people that didn't like fuzzing, they also had to stick to their motto, which is you cannot argue with a root shell. And at that point, they had to accept kind of works. The tide really started turning around 2002. This is a slide from a slide deck where Dave Eitel, who had recently quit the NSA and published a fuzzing framework called Spike, presented Spike at a conference, where he quoted a then infamous hacking group called Gobbles. I used to laugh at fuzzers, and then you changed my whole outlook of life. So eventually, when the technique generates enough results, you have to begrudgingly concede that it works, even though it didn't fit into your value system, and then you have to rebuild your value system and adjust your value system. So my personal experience with fuzzing was I wrote a fuzzer for money in late 2001. I couldn't quite understand why the client wanted it. I wrote it, was a very standard protocol mutation fuzzer. So you record some traffic, you start enlarging strings and flipping integers to interesting values. The client was very, very happy with the fuzzer. Apparently it worked very well for what the client needed it to do. I never used it myself, to the extent that I even forgot that I'd written it until many years later when friends of mine that had worked on that project on the client side reminded me that I'd done so. So at least in 2001, I was still way too invested in the value system of my youth culture to understand the value of fuzzing. And it's kind of hard to imagine from today's perspective how insanely buggy and bad closed source software in particular around 2000 was. Like the way that people fuzzed back then was literally using a scripting language called Perl, which some of you may have heard of, essentially an ancestor of Python in some sense. To manually pipe output from Perl into network daemons. So you would do essentially a Perl one-liner print A 2,000 times and then pipe that into the daemon and hope it would crash. And that is the way people would find important vulnerabilities. There was Lotus Domino SMTP server. So essentially the US Navy was running the entire email system on a server that fell essentially after half an hour of prodding like this. And was very common when you try to just write a valid client for a commercial database system at the time, that the database would just keel over when you were trying to legitimately interact with it in a friendly manner. So it was often difficult to interact with other software systems without them crashing. So yeah, another example is on 9/11, which was a fairly significant historical event. CNN.com was still being served from a then known vulnerable web server that would crash after two days of playing with it. And bugs were so abundant that hackers would often, when they found a crash that was a heap corruption, they would decide, well, this is too much work to write an exploit for. I'll just look for a Stack Overflow because it's easier to exploit. That said, not all software was terrible. OpenSSH, for example, was already considered an almost unimaginably hard target at the time. So there's a few bugs that were fuzzed that stuck with me because they had some influence on my life. The first one was a remote bug, and the only bug in history ever to be fuzzed out of OpenSSH, or the only remote bug of note to be fuzzed out of OpenSSH without a real fuzzer even. The second one was a bug that Dave Eitel found in RealServer that was just hilarious in its structure. And then there's two bugs that when I was faced with these bugs and writing exploits for them, led to research directions that led to me broadening my understanding of the topic quite a bit. So the first one is OpenSSH CRC 32 compensation attack, CVE 2001-0144. Michael Zaleski, who will play a role in fuzzing later on, had started doing security research for a company called BindView. To this day, nobody remembers what BindView did. But they did something related to security, and they were hiring security researchers. And he had just started his job, and apparently he was waiting for his corporate computer to be set up. And on his laptop, essentially out of boredom, he piped random data into OpenSSH, and it crashed. And that was this particular bug, and was a reasonably complicated and also reasonably powerful bug. So Michael Zaleski is the only person that has ever fuzzed a remotely exploitable vulnerability out of OpenSSH. And he 11 years later, he goes on to write AFL. I'm not sure whether his experience with OpenSSH helped him have the confidence to write AFL later, but it's certainly interesting that he got very, very, very lucky, you can argue, early in his life. I mean, he had great research results across the board, but the particular OpenSSH bug was sort of luck. And then proceeded to do really great things later on related to building the actual engineering for fuzzing. Another bug that I found very hilarious at the time was a bug in RealServer. RealServer was a server infrastructure that was used to stream music across the internet and radio. So you had essentially online media would use on the server side there the software to stream media to people. So you could listen to music and stuff. And Dave Attell was fuzzing RealServer, and the other software started executing his data without him trying to exploit it, which is somewhat surprising because you expect it to crash and you have to write an exploit normally. But what was happening there is that RealServer would take an incoming request, it would split it at the slashes, and then would allocate a small char buffer for each substring, and then place one after the other of the char pointers on the stack in a stack buffer of char pointers, with the effect that you would overflow the stack buffer of char pointers. That would mean you would override your existing return address on the stack with a pointer to your data. And at the time, data was still easily executable, so the server would just start executing data you sent to it, and a self-exploiting bug. I personally worked on a bug in Cisco's VPN appliances at the time. So there was a lot of firewalls at the time that implemented VPN tunneling as well, usually via IPSec, via the IKE version 1 protocol. If you ever want to read a life-changing piece of documentation, the IKE protocol specs are it. It's one of the few protocols that got simpler in version 2, because version 1 was so ridiculous. And the issue in this thing was actually a logical bug in the state machine in the implementation of the protocol, because in IPSec, you negotiate a shared secret with the other party, so much so standard. And then you can authenticate traffic integrity. You can switch on essentially, please use my shared secrets to both do encryption, but also authentication and integrity. And you could essentially, before you had fully exchanged the secret, enable, please do integrity checking of my messages now, with the effect that the server side would start calling a function called MD5 update for hashing the packet, without having initialized the data structure that manages the memory buffers for updating the hash function. The end result is it would use uninitialized stack memory, and the data structure contained a char pointer to a buffer into which to copy the data to be hashed. So if, like normally this would crash because the memory would just be 0, but if you manage to pollute the data on the stack cleverly beforehand, you would be able to give a char pointer to the device to copy your packet data into. So you had essentially write my data to anywhere in memory bug primitive. And that was very tricky to exploit, but it led me to fully appreciate the importance of non-initialized local variables at the time, and greatly broadened my understanding of how exploitation needs to work. And then there's a bug that had a big impact on my career, because I wrote a paper, like 6-7 years later, I wrote a paper on weird machines, on formalizing what exploitation actually means, based on the scars I had accumulated trying to exploit this particular bug. Because at the time, 2008-9, I was very, very busy. I had just finished my master's. I had started my PhD. I was running a company with 10 employees at the same time. It was very a very unpleasant situation. And I had also committed to finding an exploitable bug in Acrobat Reader. I had no time to read any code. Like my day-to-day was just impossible to find the focus to do so. So I worked with somebody who was bit flipping PDF files essentially and found a crash. I was like, okay, I'm gonna write an exploit for this. And then this particular crash turned out to be a little bit of a nightmarish bug to exploit, because you got to write a single byte that the attacker controlled into about a 50 megabyte memory buffer, but you had no control over where. And this memory buffer was essentially a random address on the heap. So you have your heap. There's many, many different objects there. You get to write one byte, and you have no control over precisely where. And to this day, I never managed to root cause the underlying bug, which is interesting, because normally, like when you have a fuzz crash, you have no false positives in the sense of, it's a crash. That doesn't mean you understand what's going wrong. And to this day, I never understood what was going wrong in the program. I just know I have this random write, and I needed to make do with it. And writing that exploit took a lot out of me, with, at the end of it, me giving a conference presentation at a conference called Infiltrate, and then that spinning out into what would later become the Weird Machine paper, because the bug was so shitty that I had to learn so much about exploitation that it broadened my horizon about what exploitation actually means quite a bit. So bad fuzz bugs teach you lessons. Anyhow, a common trope is that fuzzing is a little bit like applying force. If it's not working, you're not applying enough of it. And I think that's just a quote I want to throw out here, because it ties into what I'll talk about next, which are the reasons why fuzzing is successful and the reasons why we may want to look at the bitter lesson from AI. So the reality is, as much as we would like to think that human brains are the primary drivers of relevant bugs, the majority of all shipped bugs that were fixed were fuzzed. It's hard to quantitatively show this with data, because not everybody, like when a CVE is issued, nobody tells you about the methodology that was used for finding it. But this is almost certainly true. It may not be true if you attach a weight of importance to individual bugs. You can argue that, for example, the bugs that were used in Stuxnet had a higher weight than the bugs, like many bugs in FFmpeg. But if you go for the sheer quantity of software bugs being found, fuzzing is the most successful bug discovery, vulnerability discovery methodology in history. Which is interesting, because fuzzing is clearly not where most brain power went. Program analysis in general has a very long and deep history, with many, many extremely smart people spending their careers trying to write analyzers that are good at finding bugs. In the end, nothing outperformed in sheer quantity, just essentially throwing spaghetti at a wall. So what's the reason for this success? First of all, fuzzing is writing Moore's law. Improvements in the speed of CPUs directly translate into more test cases per unit of time and money, which means there's an exponential curve that is external to the research community that is driving success and progress. This is going to get exponentially better over time without you doing anything. That's a very, very useful property for any technique to have. The other part is escalating software complexity. Software, as Moore's law has continued running, software has gotten ridiculously more complex over time. But fuzzing as a technique does not get much slower as your software gets more complex. Program analysis does. So to some extent, you get Moore's law makes computers faster, software gets more complex in accordance with Moore's law, and your analysis methods tend to scale poorly in the size of the input program. So now your program is twice as complex. Any smart reasoning about the program is now all of a sudden 100x more expensive. So a beautiful thing about fuzzing is it doesn't care about the complexity of the program you're fuzzing. It just runs. The biggest lesson, well, one of the biggest lessons, horizontal scalability. I had understood horizontal scalability in the late 2000s, but I got hit with it in the face when I joined Google in 2011, when they acquired my first company. Google was all about horizontal scale, and they just had massive amounts of compute. And Google was a very classical environment, which was not really compute bound, but usually brain power bound. And they were very good at doing it. So the thing is, of all program analysis techniques or all bug detection techniques, fuzzing is the only one that is absolutely trivial to distribute horizontally. More machines, more fuzzing, more results. Very, very simple. And this ties into Moore's law, because Moore's law topped out when it comes to single core performance at some point. So most of the chips can't make the individual core faster, they can just give you more cores. Well, if you're doing, let's say, abstract interpretation, actually doing this on a multi-core system while utilizing all cores to the fullest is already difficult. Let's not even talk about multiple machines. Fuzzing distributes really nicely with this. And that's a very important property to make use of Moore's law again. And then there's something where it's in AI, there's something called the hardware lottery, where people say, got hardware that is specialized for a particular machine learning model. They'll be so fast that overcoming the limitations of that model in software will have to make you, like a model needs to be, or the new technique needs to be like 5x better, like a 30% improvement doesn't cut it because you've got this big hardware advantage. And it turns out that CPUs are designed to do CPU things, which is executing code. So from this, every person that does fuzzing has dedicated hardware to do fuzzing, because a computer will execute things. You're using the computer for what it was designed. If you think about any clever program analysis, where you do any form of interpretation of the program on a more, like on a higher level domain, where you summarize states, clearly that's going to be more expensive than executing a single instruction in the CPU, because you'll need hundreds, perhaps millions of instructions to perform that operation in the abstract domain. Which means any improvement in smarts of your program analysis methodology needs to be good enough to make up for that hardware deficit. So you need like a 30% improvement doesn't cut it. You need to be 100x more effective to pay for the cost of your more expensive compute. A big thing for industry was the lack of false positives. Like all the static analysis tools that reasoned about code were essentially hated by all the developers, because a developer doesn't want 50 false positives. Like in essence, you give a developer 5 false positives and he'll never trust the tool again, because it takes a lot of effort for the dev to actually look into the code and see whether it's real or not. So the thing that everybody in industry, both on the attacker side and on the defender side, loves about fuzzing is, if it crashes, you've got something. There's no wading through large quantities of false positives. And turns out that because we came, like a lot of program analysis came from a software verification perspective, where they wanted to prove absence of bugs. What people wanted more than absence of bugs, obviously, is absence of false positives, which, yeah. Okay, another thing that is not to be neglected is fuzzing had good, widely available implementations. Implementing any technique, no matter what its tailwinds are, requires a good engineer or good engineers that invest time to make good engineering decisions and build something. And fuzzing had, well, particularly AFL had outsized impact on fuzzing as a field, because Michal Zaleski is an excellent engineer, and he made very, very smart engineering decisions in designing AFL that really played to the strengths of fuzzing. AFL was designed to just work with minimal setup. It was had many design decisions internally that were very focused on preserving performance. Because people had done coverage-guided fuzzing before, but they had set breakpoints in the program or done other things that imposed such a high cost in terms of computation that the gains from the coverage weren't worth the cost. So if you're paying a breakpoint and a context switch for every new basic block you're hitting, your fuzzer will be slowed down by this process so badly that you may be better off just fuzzing without feedback. So AFL made the good design decisions that allow the techniques to shine, but those were largely decisions about how can I get the benefits of this technique without paying too much computational overhead to eat up the benefits. Then there's another thing that's not to be underestimated. Fuzzers are relatively simple designs. The industry does not, by and large, invest 30 engineer teams for 2 years into writing fuzzers or program analysis tools. So the implementation complexity of fuzzing was sufficiently low that a small number of engineers could actually write software that did all these things and was impactful. So the implementation complexity to benefit calculus in fuzzing was always very favorable. Okay. And I think these are the 7 reasons why fuzzing was as successful as it was. And I've mentioned the bitter lesson in AI multiple times now. And it's the bitter lesson in AI is a very influential article from 2019 about AI modeling, which essentially says, because of Moore's law, any smarts we've tried to put into any AI algorithm at any point in time usually gets outperformed by just sheer scaling of compute over time. And it's sad because in the lifetime of the individual researcher, that's where you let's say Moore's law grows compute at what, 30% a year. So in the lifetime of a research project of perhaps a year or 1.5 years, 30% isn't all that much. Over a period of 6 years, it compounds massively. So the dynamic in almost all of AI was that people tried to be clever. People tried to put more of human ingenuity and understanding into the ML algorithm. And it locally was enough to demonstrate a local improvement of sort. But then it scaled poorly as more compute became available. And over a period of 4 to 5 years, it was completely irrelevant. And the field routinely has gotten better by being dumber. Dumber in the sense of trying to be less clever. And the bitter lesson it's a great article. I can just recommend read it. It shows that humans have a bias towards wanting to believe in your own ingenuity. Like the hacking scene youth culture wanted to believe in their own smarts, when the more effective thing was more compute. Be like look at what you're doing, try to make it simpler, try to make it dumber. So what I'm pondering what I was pondering as I was writing this keynote is perhaps fuzzing is really the bitter lesson for program analysis, where the thing really is, if we care about finding bugs, perhaps the trick really is try to not be clever. And if we look at what the AI community is doing, is they're like, since this article, they're all in on just compute and scaling laws. Scaling laws meaning we make it bigger, we compute harder, it'll get better. And that has led to the industry being transformed, where they're throwing hundreds of billions into compute infrastructure. And it interestingly transforms the nature of a lot of the research being done there, where it gets mutated from trying to model more smartly into systems engineering, try to build larger systems that can shuffle more data around, that can do more compute for the same power envelope. So it really changes the nature of something that could be deemed adjacent to fundamental mathematical research to how do I build the biggest power plant that pipes the maximum amount of power into these transistors to do what I want to do. And one of the things that they say in the bitter lesson is the 2 methods that scale arbitrarily are essentially search, which means brute force exploration of a state space, fuzzing, and learning, which means largely stochastic gradient descent to and auto differentiation to adjust parameters. But search is very, like, search in the machine learning sense and the reinforcement learning sense is very, very similar to fuzzing. Like, you stare at it and you're like, this is the same. We just have different vocabularies. So reinforcement learning and fuzzing are actually, if you stare at what you're doing in a reinforcement learning algorithm, it's really, really similar to what you're doing in a fuzzer. And all of AI has depended in recent years to do brute force search to some extent. Deep Blue for chess was largely about large-scale chessboard exploration. And a lot of computer chess researchers were very dismayed by the approach of just throw more compute at it, because they tried very hard to encode more understanding of the game into their various game models. And the trick was throw compute at it. AlphaGo, very similar thing. The real breakthrough was use an image recognizing neural network to value a very large scale exploration of the board states. And if you look at the LLM community, there's a universal agreement in the LLM community at the moment that the next evolution in LLMs is going to come from integrating some sort of search, RL style search into the design. And the last OpenAI release last week of the Strawberry model does precisely this. So And reinforcement learning for playing computer games, for example, is very, very similar to fuzzing. And I think it's beneficial for the fuzzing community to stare more at what RL is doing. Because they do something, for example, like novelty search. Novelty search in a computer game is you've got a computer game, you're trying to train an agent to play this computer game. But the computer game, like the objective of the computer game is not necessarily even clear. So they're trying to find the minimum number of things they need to do to reach a state they've never seen before. And if you stare at it a little bit and look at code coverage metrics in fuzzing, that's kind of the same thing. We're trying to reach more novelty in what we're doing. There's one big difference. In reinforcement learning, you're doing all this exploration to then train an agent to play the game again. As a fuzzer, you really don't care to play the game ever again. Like if you manage to crash the computer once playing this one thing, that's fine. Because we don't really use a fuzzer on, let's say, one mail server and then try to run the output on the other mail server all that much. So what I'm saying here is that with all my me raging here that fuzzing and RL are really related, it's also important to remember the differences because those differences matter. So I mean, we've all been in a place where we've run a fuzzer and then at some point code coverage as a metric starts tapering off and just saturates. It seems that your fuzzer cannot break through the wall of some state machine inside the software to reach more stuff. Part of the problem is something that I call the implicit state machine. It's when you write a piece of software, you have essentially an FSM in mind that you're implementing. And with a pure code coverage metric, you will not understand that, oh, in order to unlock this new field of new code that I can reach over here, I first have to go down here to switch a variable, and then I have to go down here to switch a variable, and then I can explore up here. So in some sense, code coverage is blind to the state machine that is actually being implemented. And this gets most drastic if you actually think about game playing and fuzzing. Imagine, I'm not sure whether one of you has ever written a small game, but games are very standardized in they have a game loop. The game loop runs to update all the state of the game objects. So it iterates over the game objects, updates their states, draws the next frame. And then again, so a game, like the code of a game is often relatively small in the sense of you only have this tight loop that always goes in a loop that needs to be done by the time that the next screen has to be drawn, and that updates all the game models. So you can see here that a code coverage metric would not explore much of what the game offers, right? Because you would have covered the loop relatively quickly in relatively short time. But really all the novelty in the game happens not through code coverage. And I think that may be an interesting lesson to think about when you think about fuzzing, particularly as we're moving to more memory-safe languages, where finding a crash is not going to be happening anymore, and finding novelty, finding behavior that's not supposed to be there or that is in violation of your assumptions is important. At that point, you're looking at something like novelty search in a game. Anyhow, so perhaps we need to model the internal state machine somehow, but didn't I just say that trying to be clever is usually a loss? There's a German expression called Stumpf ist Trumpf. Stumpf meaning blunt, but also meaning stupid. Trumpf being in a card game, the trump card. So, and there's a German rap song which has as a refrain, ich hätte, könnte, würde, aber stumpf ist Trumpf. I could have, I should have, I might have, but really stupid wins. So perhaps before, like I would like to think about, we need to model the internal state machine better. But perhaps we just need to go faster. Perhaps you don't need to be clever. And then the question becomes, what, I don't know, but what I would find interesting is as a research question, what are my current fuzzers bottlenecked on? Where am I spending my time when I'm fuzzing? How can I make this go faster? And looking at GPUs and GPU design and how they make use of parallelism, can I build dedicated hardware to fuzz much faster? And now a crackpot napkin math idea. Let's say I want to fuzz a smaller class of software, not generic software. Let's just say I want to fuzz image codecs. Image codecs have the property that I usually have perhaps a megabyte of input perhaps 20 megabytes of output, something along those lines. That's a reasonable assumption. I don't need gigabytes of memory for that. Let me think about how can I build a GPU-style design, or what would the corner points of a GPU-style design for fuzzing an image codec look like? Reasonably small input, reasonably small output. How do I maximize parallelism? Now, we have consumer devices, Apple's M2 Ultra, that ship with 134 billion transistors in a consumer device. A small RISC V core has about 20,000 transistors. For those of you that remember the Amiga and Atari ST, I see people in the back. It was driven by a 68K CPU. The 68K CPU was called 68K because it had 68,000 transistors. So we can put 1 million RISC V cores or 1 million Amigas on the real estate of a single chip, like 1 million machines that can play, like that had no problem playing Mario World or Jana Sisters or whatever. So we put 1 million of these cores on a single chip. We still have 66 billion transistors left. At this point, we don't need DRAM. We can put 64 megabytes of SRAM on the same chip for every core. So now we've got 1 million cores, each with 64 megabytes of RAM, all of which I can run the same software on, except with 1 bit in the input flipped. So in essence, I have the same state duplicated. I initialize 1 million cores with 1 million times 64 megabytes of RAM to the same state. And then I start clocking them, all at the same time. And if you look at the way that GPUs harness the parallelism, they do stuff like many, many different cores will share the same instruction stream as long as their instruction pointer is the same. And they will just stop cores when they diverge and then resync them as they clock again. So I've got 1 million cores. They each have 64 megabytes of RAM. I've got the image codec started on each of them. And I start clocking them. And I share input streams. And in 64 megabytes, I can run, there's a Linux, there's a Ubuntu distribution you can run in 64 megabytes of RAM. So clearly you can run your image codec in that. So I can run a stripped down version of my operating system. I can run an image codec. And I can try to harness parallelism in the same way as a GPU. And now I can even think about deduplicating RAM pages because a lot of the RAM in almost all these cores will look the same until they diverge. So I can now bit flip every single bit, because I've got 1 million cores, in a 128 kilobyte input file at the same time in a different programming run. So I've got a 128 kilobytes input image. I just clock 1 decoding run for this image. And I have flipped every single bit in 128K in this one go. And at least on paper, like all the actual chip designers and electrical engineers are going to scream at me and you're like, you don't know what you're talking about, which is true. But on paper, this at least looks like I can make things go faster here. And yeah, I guess the question then becomes, where should resources be applied? We've got this brain power that wants to apply themselves to fuzzing. Apparently, there's people in this room. And then the question is always, should you be more clever, or should you try to be stupider but faster? And the one is a question of better modeling of the reality by human brain power. And the other one is building better systems that can just go faster. And it's really unclear whether the trade-off is. And I think that's also a lot due to individual preference. But my advice would be, as a young man who had a value system that valued being clever, and then had to accept over time that being fast and stupid is more effective. Be aware of your bias towards trying to be clever. And in case of doubt, overcorrect towards being stupid but fast. All right. Thank you for listening. Any questions?